Guys, in this video we will be deriving the Arrhenius law, and it's a very simple derivation, but somehow it's not given on most of the websites on Google, and also no any YouTube video is available, and even some authors go up to saying that it's an empirical equation and it cannot be derived using any such laws. Well, they are partially true, because here we will be deriving the equation using the thermodynamics, and we will be using the Gibbs free energy equation for that. We can directly also start from the want of equation, and yeah, so let's begin. Guys, please bear in mind that some construction work is going on nearby my place, and I'm no good professional editor, so you will have to tolerate that. Okay, so first of all we will be starting from the Gibbs free energy equation, which we can write as delta G is equal to minus RT ln K, which is nothing but a special case of Clausius-Clapeyron equation. We also know that delta G, which is Gibbs free energy, we can write as delta H minus T delta S, where delta H and delta S are change in enthalpy and change in entropy respectively. Now we will have to rearrange this equation, so let's bring that minus sign along with minus RT to the left hand side. So we will get minus delta H upon RT plus delta S upon R is equal to ln K. So now what we will do is that we will differentiate this equation with respect to t. So while differentiating, you have to note that this whole term delta S by R will become 0, because we know that delta S is a function of t, but when we divide it by R, that is the gas constant, it no longer remains a function of t. So differentiating with respect to t will, for a constant, gives a 0. So differentiating with respect to temperature, we get delta H upon RT square, because 1 by T is minus 1 by RT, so is equal to D, let's write ln K upon dt. Okay, nothing fancy here, we all know how to differentiate simple things, and this equation is actually called the Hoff equation, very famous equation in thermodynamics. Now before proceeding, we must know how to deal with this capital K, because we need the Arrhenius equation in terms of radical constant, and this capital K is the equilibrium constant. So for that we will write the reversible reaction of A goes to R, where the forward rate is given by small k1 and backward rate constant is given by small k2. Now the rate equation for this reaction can be written as minus RA is equal to K1 CA and minus K2 CR. Now at the equilibrium, the rate of any reaction becomes 0. So minus RA, let's say at equilibrium, becomes 0. That is K1CA is equal to K2CR E. That is for equilibrium. From here we can write CRE upon CAE is equal to small k1 by small k2, and which will be equal to our capital K. This is how we will relate the equilibrium constant to the rate constants. let's give this equation number 2 and the want of equation number 1. Now if we put the value of capital K from equation 2 into the equation 1, we get d ln small k1 by small k2 upon, sorry for the camera angle, dt is equal to delta h upon RT square. We can also write it as d ln small k1 upon dt minus d ln small k2 upon dt. Nothing special, just the property of logarithm. And let's give this equation number 3. Now guys, we want to replace our enthalpy term with the activation energy term, and for that we will have to use the plot of activation energy and the distance along the path. These two plots are the left one for the endothermic reaction and right one for the exothermic reaction. That's why delta H negative on the right hand side and positive on the left hand side. So as we can see in the plot, the difference in the energy values, here you can say E1 and here you can see E2. So E1 minus E2 can be written as delta H value. So if we use this in our equation, we can replace enthalpy with the activation energy, and these are standard plots of, so these can be found in any literature of chemical kinetics. So let's write our equation. We had d ln small k1 upon dt minus d ln small k2 upon dt. Now in place of delta H upon RT square, we will write E1 upon RT square minus E2 upon RT. Comparing the same subscript terms and writing the equations individually, we get d ln k1 upon dt is equal to E1 upon RT square, and from here on integrating we get ln small k1 is equal to minus E1 by RT plus C. Now on taking the log term here, it will become the exponential, so you will get e to the power minus E1 by RT, and we will also get e to the power C, so you will write it as another constant, that is k0. So there you have it. This is the basic form of Arrhenius equation, and similarly for K2 we can also write ln K2 is equal to minus E2 by RT plus C, and we will get K2 is equal to e to the power minus E2 by RT into K0. And on dividing this equation by this, we can get it in the standard logarithm form again.